Okay, so this is the problem that we would like to attack. We have a spherical mass, and we would like to find the forced gravitational attraction it creates for a point mass outside the spherical shell. So we divided this spherical mass into spherical shells, and now we divided these spherical shells into spherical rings. Now we had already finished the gravitational attraction of a spherical ring. Now comes the point, what about the spherical shell? Now the shell we can construct just by combining rings of different sizes. And that is what we will do. We have this spherical shell. We divide it into very narrow rings. Okay, I just made some definitions. The distance of this strip of this ring from the center of the sphere, I call it K. The distance of between my point mass and the center of my sphere, I call it R. So what remains is R minus K. The width of this ring is dk. And, well, this is L is the distance from my mass to the edge of the ring, to any point on the ring. And R tilde is the radius of my ring. Now we can just write, okay, and there is also the angle theta. Angle theta is the angle between this line connecting the center to the edge of the ring and the line connecting the center of my sphere to my point mass. That is how I define the angle theta in this case. Now we already had derived the expression for the force created by the ring. So if we have a ring of mass m, then we know that this is the force that it creates. Now first we have to express the mass of this ring then. Now the mass of the ring, let's call it m dm. It's a very small mass. Since it's a very narrow ring, it will have a very small mass. It is nothing but the area of my ring divided by the area of my sphere. This is the fractional area of my ring, times the total mass of my sphere. So I'm assuming that the mass is distributed uniformly over the surface of the ring, or over the surface of my sphere. Now the area of this ring, if you just take this ring, open it up, it's almost a rectangle, a very long rectangle. This is my ring. If you just cut through one point and open it up, the thickness of this ring will be just dk. And the length of this ring, this rectangle, is 2 pi r tilde. It is the circumference of my ring. So the dA is just the product of the two, 2 pi r tilde times dk, divided by the total area of my sphere is 4 pi over 3. Well, the radius of my sphere is small r cubed, times the total mass. So the mass of my ring, I can just write it as 3 over 2, the radius of my ring, times the mass of my sphere as a whole, times the thickness of my ring. This is one expression I have for the mass. Well, since I now know the mass, I can just put this mass expression to here to obtain the force created by this ring only. So this force, well, it will be in the z direction, so I'm only writing the z component of the force, minus gn, the mass of my point mass, times the mass of the ring. It is this dm, 3 over 2 r tilde m dk. So I don't have it over here. Okay, this is what I had. I have the Newton's constant, the mass of the ring, I already wrote it down, my point mass. Well, this L is the, well, I can use this expression over here. L is the distance from the center of my mass from the center of the ring. So that is In this example, it is just r minus k divided by, now multiplied by r minus k divided by d cubed, d being the distance of my mass from the edge of my ring. And in this example, I denote it by small l, l cubed. Now, if you look at this expression, this is kind of complicated, because as you change your ring, this is one ring at a distance k. If you take another ring, in that case, k will change. Okay, this k will change, l will change, and theta will also change. So everything is changing. So you have three parameters, expressions appearing here, which are all changing depending on which ring you are considering. So in such a case, it's best to just fix one parameter and express everything in terms of that parameter. So now we would like to express all of this in terms of a single parameter. Sorry, I have some mistake over here. Okay, here I forgot the, sorry. Now the area of my sphere is not 4 pi over 3 r cubed, it is 4 pi r squared. So if it is 4 pi r squared, I have r tilde m over 2r. This is my mass. Okay, so this is the mass of my ring. I have the force created by this ring only. Now the next thing is I have to express all of these variables, my k, my l, and my theta, in terms of a single variable. And then I will be summing over all that variables. Now it turns out that in this case, the simplest variable to choose is L. We will try to express everything in terms of this L over here. So I have to express K in terms of L and theta in terms of L. And these are the expressions I have. Now K, if you look at this K over here, this is my angle theta. So K is nothing but the radius times the cosine theta, or cosine theta. Now L, here you can take this triangle over here. I have this triangle. This angle over here is theta. So I can write L. It's just like the Pythagoras theorem for non-right triangles. So does anybody know how to derive this relation? Does anybody know about such a relation for an arbitrary triangle? If theta is 90 degrees, then it is a well-known Pythagoras triangle. The hypotenuse squared is the sum of the squares of the right angles. But if the sides are not right, but it's not 90 degrees, but it has an angle theta between them, so this is still an expression you have. So how many of you knew this expression before? So how many of you know how to derive this expression? So how long does it take? Okay, so okay, that is the point I would like to make. So does anybody try to prove this without using vectors? It takes pages. With vectors, it is just 2 lines. So let us see that. I mean, just because you learned vectors in physics courses doesn't mean that you use vectors only for physics courses. You can use vectors for anything you like. It is just a tool we have. So this is the triangle we have. This side has length r, this side has length capital R, both of which are fixed, and this side has length L. And this angle over here is theta. I will just invent some vectors. This is my r vector. This is my capital R vector. So R vector points in this direction and has this length, small r vector. Capital R vector points in this direction and has this length. And then I can invent this L vector, which points in that direction and has the length of L. Now this L vector, I can just write it as capital R vector minus the small r vector. Because, or like, if you like, if you have the small r vector plus the capital L vector, so you are moving from here first to this point, then from this point you are moving to this point, but that means you are moving from this point to this point, that is your r vector. If you just move the small r vector to the other side, this is the equation you have. Now, L squared is nothing but L vector scalar product with itself. If I use this expression, this is equal to capital R vector minus small r vector squared. If I take the square of this expression, it is the square of this one, which is r squared, plus the square of this one, small r squared, minus twice the scalar product of these two vectors. But if you remember this definition of the scalar product, r squared, capital R squared plus small r squared minus twice the scalar product we had defined as the product of their length times the angle between them. Well, the angle between them is theta, cosine theta. So that gives us a relation between this angle theta over here, the radius of the sphere, and the distance of my mass from the center. So I have that expression over there. So, okay, this was my force. I'm trying to express everything in terms of L. That would okay, so L squared is equal to r squared plus capital R squared minus 2 capital R small r cosine theta. But note that k, this k over here, is nothing but small r times cosine theta. This is my small r, this is my small r, and this is my k, and this is my angle. R times cosine theta is my k. So this here is k, which tells me that k will be equal to r squared plus capital R squared minus L squared divided by twice dr. I just move this term to the other side, L squared to this side, so that's why I have this minus L squared divided by 2r. That will give me k. So one task I'm already done. This is the force I have, I'm trying to express. If this is the force I'm trying to express, I have to write k in terms of L. That is done. Well, kind of, I'm done, I think. If k is this one, dk is nothing but, do you understand this notation, dk? So it just means that, so let us look at this one. Let's look at delta k. Now, k depends only on the variable L. Now, the question is, if I change L by a very small amount, how much does k change? So if I change L by somewhat, delta L, the change in delta k, in k. So this ratio, well, we know that this is nothing but the derivative. So you should, okay? So this is the derivative. Yes, question? Which one? This 3 over there. Well, that is a mistake I did. This is r tilde m over 2r dk. So I have already expressed k in terms of L. L is already there. Now this dk, that is, in each ring, I'm changing k by a very small amount, by that dk. But as I'm changing k, I'm also changing L. Because if I take the next ring, L will be different. L will be L minus delta L, some very small amount. So rather than summing over different values of k, I would like to sum over different values of L. But then I have to express this change in k in terms of the change in L. That is what I have to do. Well, this ratio, the change in k over the change in the L is nothing but the derivative of k with respect to L. I have this k as a function of L. If I take the derivative, I have, well, these are just constants. The derivative of L squared is 2L divided by 2R. This is minus L over R. This just tells me that if k changes by this much and L changes by this delta L, they are related. Minus L over R times delta L. If I make these changes very, very small, it's just a notation. Delta k just becomes dk, and delta L just becomes delta L, dl. So here, at first what I did was, I was labeling each one of these rings with their distance from the center, k. And each ring, each neighboring rings, they were differing in k by dk, the width. Now I'm labeling each one of these rings by their distance from my point M. And each successive ring will have an L value which differs from the previous one by dl. Now, this is my dk. The change of k from this point to this point. Now I know how to relate that change to a change in L, because this line over here will have one L value, this line over here will have another L value. So L value between these 2 points will be different, just like their k values, and the two changes are related by this expression. Now this minus sign just tells me that if I'm increasing the value of k, well, I took the positive k in that direction. So increasing the value of k means going from here to there, but that means L value is going from here to here. L is decreasing. So that is why I have that minus L over there, minus L over R. Now I'm considering my rings. I have this ring, the second ring, the third ring. I'm summing over all these rings starting from here, and I will be moving up to this point. So if we just combine everything, now we are just combining the things we have. We have the Newton's constant, the mass, my point mass. I have this, okay, one more thing, R tilde. I still have to express R tilde in terms of L. That I didn't do yet. But note that R tilde is R sine theta. So let me just erase here. Now R tilde is R sine theta. This is one thing I have. Sure. Well, everything is changing. As I change my rings, theta is changing, k is changing, L is changing, everything is changing. Only one, we are trying to relate all those changes to a single parameter. And in this case, we chose it to be L. So I'm not yet done. So I know that, okay, what we have done, I know that R tilde, this is constant, but R tilde is changing with theta, and theta is changing as I change my L. So I have to find the relation between sine theta and L. So how is R tilde changing with L? Well, what we can do, well, I know how k is changing with L. So I can just write, if you like, R tilde as square root of R squared minus k squared. So it just replaced the dependence on theta with k, but I know how k changes. K is given by that expression over there. R squared minus Okay, k squared is r over 2 plus r squared minus l squared divided by 2r squared. So here is what you were looking for. But I think there was a simpler expression for that. No, we seem to be missing something. Well, that's what we have. I will check my answer over here. Now, this should be the answer we have. R tilde should here, in this way of deriving, I had an R tilde, 1 over R tilde. Okay, whatever. We have this R tilde. Okay, this is our R tilde. Now I don't see how. Okay, you should just take this thing, put it over here, and at the end of the day, what you have is you have these factors. Okay, we have the R tilde over there, R tilde times R minus K. Okay. You have the R tilde expressed in terms of L. Delta K in terms of L, expressed in terms of L. R minus K, well, we have already expressed K in terms of L over here, so R minus K we have in terms of K, in terms of L. L in terms of L. Everything is now in terms of L. Now the force due to this ring now turns out to be some function in terms of L. Well, you have all these terms, this term, this delta K, this L over R over here, this dk, R minus K in terms of R, everything multiplied by dl. So this is the force created by the ring located at a distance L from my mass. The edge of the ring is at a distance L from my mass, and the thickness of this ring is dl. Now what should I do is just sum over all these rings. So I should sum over all possible values of L. So the force, the total force acting on my mass will be just the sum over all possible values of L of this function that I have times dl. Now my L, what are the possible values of L? If I'm out of the ring, the minimum value that L can have is capital R minus small r, and the maximum value that L can have is capital R plus small r. When I am summing over all these values of L, I have to sum over all values of L between these two limits. So in the limit that I have this thickness of my rings infinitesimal small, this just becomes an integral. So this is an integral of this, whatever this function is, the L which goes from capital R minus R to the capital R plus r. This is the value I have. Now, this is for out of the ring. Okay, so if you are out of the ring, L goes from capital R minus small r to capital R plus small r. Now, if you are in, which will give you this answer. Okay, you have all these complicated expressions, but if you are able to evaluate that integral, this is what you will get. If you are not able to evaluate that integral, then there is a computer programs which allow you to integrate those integrals, which is this expression over here. Now, if you look at this expression, this is nothing but the gravitational attraction between two point masses whose distances is r. Now, if you are inside the ring, so this is inside your sphere. If you are here, the minimum, the L, at this point, L has a value small r minus capital R, and at this other end, L has the value small r plus capital R. So whether you are inside your sphere or outside your sphere, the possible values of L is different. So these are the limits of your L. And it turns out that if you take this integral, you will get 0. So we know that outside the sphere, it just acts like a point source. If you are inside the sphere, you will feel no gravitational attraction. It is in a sense similar to the ring example. Remember, when we studied the ring, we said that if you are right at the center of the ring, you will not be feeling any gravitational attraction. It was mainly because the masses at opposite ends on the ring will just create equal forces in opposite directions, so the gravitational attraction will cancel. Now, in this case, it's a bit more complicated. If you are inside this ring, inside the sphere, you can imagine that you divide the sphere into two. This part of the masses, this part of the sphere, will create a force in this direction, and all the other parts of the sphere will create a force in the opposite direction. Now, this part of the sphere in this case is smaller. You have less mass here, but the distance of the masses from your point mass is also smaller. Since you have less mass, you should expect a weaker gravitational attraction. But since the masses are closer to you, you would expect a larger gravitational attraction. So these two effects just balance each other. On the other side, you have more mass. All of this mass is creating an attraction toward that direction. But you have a larger mass. But what happens is this mass is further away from you. So they create a weaker force. So these two effects, having more mass at a larger distance or having less mass at a smaller distance, they just balance each other, and you end up having that this force created by this mass is equal to the gravitational attraction created by all the rest of the masses. And you end up having 0 gravitational attraction inside your sphere, inside your shell, spherical shell. Well, this was kind of wake you up. Do you know the story of the planet Vulcan? So how many of you knows where does this planet come from? So you have heard the planet Vulcan, right? You have heard of Mr. Spock? Yes? What is the origin of this planet Vulcan? No, it doesn't come from the Star Trek. The planet Vulcan existed before the Star Trek. Now you see, we studied Kepler's laws. We said that the orbits have to be ellipses. And from that, we show that the gravitational attraction is 1 over L squared, 1 over R squared, right? But the gravitational attraction, if you imagine Earth, so this is the sun, this is Earth, orbiting the sun. Well, there are all other planets around. Let's say Jupiter is somewhere over here. Earth is rotating. It has the ellipse as a major axis. Now, if you look at the gravitational force acting on the Earth, there is the attraction of the sun, which should result in an elliptic orbit, but there is also the gravitational attraction of Jupiter. There is a perturbation on the orbit of the Earth caused by Jupiter. And this perturbation just, for an ellipse, this axis is fixed. It cannot change. But due to Jupiter, this axis itself is rotating. So the orbit of Earth is not exactly elliptical. It's almost elliptical. It just fails. So it just rotates. This major axis of Earth, and any planet in fact, is rotating itself because of these perturbations. Now I think it was Uranus which was discovered like this. There was some anomaly in the orbits of some planets, and scientists just went out and calculated the possible cause of that anomaly, that's observation, and they conclude that there should be another planet which is exerting a force on the, I think it was the anomaly in the Jupiter caused by Uranus. So, and they discovered that the Uranus has to be at such a distance from the sun, and when they looked at that distance, they discovered another planet there, just by looking at how the orbit of the Jupiter changed with time. There's a similar anomaly for Mercury. It is the planet closest to the sun. So people observed its orbits, how the orbit changed. So they couldn't explain the variations in the orbit. So they just postulated that maybe there is another planet that we don't know yet. They went out and tried to calculate its position. They calculated the position of this hypothetical planet, which turned out to be inside the sun. It has to be inside the sun to explain that anomaly. And the name that was given to that planet was Vulcan. So that's why the planet Vulcan is so dry and so hot in the Star Trek movie. That's the first, it was a planet hypothesized to explain the behavior of the orbit of Mercury. Well, of course, later on we could explain the anomalies in the orbit of the Mercury using Einstein's general theory of relativity. We don't need any Vulcan planet anymore. Okay, so we have calculated this. It was a long, kind of boring mathematical derivation. And if you imagine there are no planets with spherical shells inside. So what is the use of all these things? Now let's look at this dark matter problem. Yeah, you have probably heard of dark matter, right? So how many of you heard of this dark matter? Okay, so you have heard of the problem. So the origin of this dark matter problem is observations made on galaxies. Just take any galaxy. You can model it as a sphere. It's just a very crude model, a very simple model. Just model it as a sphere. And in this galaxy, just look at one of the stars at a distance r from the center of the galaxy. Now the galaxy is rotating around its center. But we had just proven that if you just divide this sphere, which we use to model the whole galaxy, into a sphere with a radius small r and the remaining shell. Now we know that this shell since our star is inside this shell doesn't exert on the mass on my mass m. This outside shell doesn't exert any force. It's only the inside shells over here that exerts a force on my mass m. And the mass of this inside sphere, I can calculate it as the volume times the mass density. So this is the mass that is exerting a gravitational force on my star with mass m, and this force is towards the center. If we write the gravitational force due to this mass, it is just the Newton's constant times the product of the mass of my star, the product of the mass inside this sphere of radius r, divided by r squared. This should be equal to the centripetal force. It is doing almost uniform circular motion, so it has an acceleration given by v squared over r. So this should be the force acting on it. So the source of this force is nothing but this gravitational attraction. So we have this relation. If it is moving with velocity v at a distance r from the center under the influence of the gravitational attraction, so we should have this relation. It just means that the speed of my star around the center of my galaxy is proportional to its distance from the center of the galaxy. So if I measure not just one star, but if I measure the speeds of many stars inside the galaxy, and then I should discover that their speeds should increase linearly with the distance from the center of the galaxy. And well, this is the proportionality constant, but for us it will not be important. Now, if you take not this star, but if you take a star outside my galaxy, right at the edges of my galaxies, then all the mass of the galaxy is creating this gravitational pull. So the Newton's constant times the mass of my star times the mass of my galaxy, for the volume of the galaxy times the mass density, divided by r squared. R is still the distance of my star from the center of the galaxy, should be equal to mass times v squared over r. And this tells me that for any star that is out of the galaxy, the speed of that star should change as 1 over the square root of the distance. So this is from our basic knowledge of mechanics and circular motion and gravitational attraction. This is what we should see. If we don't see this behavior, then we know that there's something wrong. Well, this is what we would expect. Until the edge of the galaxy, it should increase linearly. And out of the edge of the galaxy, it should drop as 1 over square root of r. This is a very crude model. This is an actual observation of this galaxy. It is called NGC 3198. This is the first one I found. These points over here this is the graph of the speed versus the distance from the center of the galaxy, of stars in this galaxy. Now you see that, well, this is probably the edge of the galaxy, about some 9 units. Until the edge of the galaxy, the speed just increases linearly, as we expect. This is the linear dependence. Now, this is what we would expect if the only mass of the galaxy is what we see, so-called the visible matter. There are all stars over there. We can just look at the stars. From their light intensity, we can extract their masses. So from their masses, well, in this diagram, we just assume the uniform mass density until the edge of the galaxy, and then it's 0. But this is a more realistic model. But nevertheless, you see the general behavior. It should increase linearly from the center of the galaxy towards the edge. Beyond the edge of the galaxy, it should go as 1 over square root of r. Now, this curve is just 1 over this behavior, 1 over square root of r curve. But this is the actual observation. It does increase more or less linearly, but after the edge of the galaxy, it stays almost constant. Well, what does it mean that as you increase r, the velocity is still constant? Remember, the acceleration is v squared over r. R is increasing, but velocity, its speed, is larger than what we would expect from the visible mass. But if the speed is larger than what we would have expected, it just means that its acceleration is larger than what it should have. If its acceleration is larger than what it should have, it means that there is a larger force acting on it than what we would expect based on our observation of the visible stars over there. So the gravitational attraction exerted on these planets outside the galaxy is larger than what we would expect based on the mass that we see in the galaxy, see in the sense of the visible light. So one interpretation of this is that maybe there is some more mass which we cannot see out of this galaxy. There's some matter over there, but it's not visible, it's not emitting light as the stars. So that's why we call them dark matter. So this is the origin of the dark matter problem. So we have this observation which doesn't match with our expectation. So we should find some explanation for this. One possibility is that, okay, there's some matter which we do not observe. This is the dark matter. Well, there are all kinds of other theories trying to explain this. Some people are even claiming that Newton's dynamics are not correct. Because remember, this expectation is based on the law that force is equal to mass times acceleration. If that doesn't hold, then we should modify our expectation. Now, there are some people working on that, so-called modified Newton dynamics. Another explanation is this dark matter. Well, of course, they say that there is no dark matter. It's just our knowledge of the dynamics is not sufficient yet. Some other people say that, no, Newton's dynamics are correct, general relativity is correct, but there's some matter which we cannot see. Well, this is one of the still unresolved problems. If there is dark matter, at least we are trying to observe that dark matter on Earth. It should be everywhere, even on Earth. So somehow we are unable to detect any presence of dark matter. But there should be something there to explain this unexpected behavior. Well, you see, it should work in our solar system, but how do you detect it? It is much smaller than we are able to detect. Well, one problem is, in fact, as you said, if there's dark matter all around these galaxies, including our Milky Way, there should also be dark matter on Earth passing through us. So we should be able to detect it. Now, currently, we couldn't detect them at all. We are looking for it, but there are no signs of them. Then there are other people claiming that, okay, we are not so lucky, we are in a region of our galaxy which doesn't contain lots of dark matter. So, well, if you buy that argument, that is an explanation, a possible explanation. Now, this is one of the unresolved problems. What do I think about that? Well, I'm kind of conservative in the sense that I trust the physics that we already know. There are some other people trying to look for explanations of this dark matter in the sense, some exotic state of matter which is invisible to us, but it is made of the materials that we already know. I would be more happy if that turned out to be true. But there are not many people who works along those lines. Questions? Well, before you go to a break, well, just for you to note, if you had asked more questions, I wouldn't have had time to make this quiz. Your questions have priority over quizzes. This system is in space, far, far away from any other planet and galaxy, so there's no gravitational force, there's no friction, so you just attach a mass to the end of a string and rotate the mass. So question 1, draw the free body diagrams. Well, this is almost identical to your second quiz. Draw the free body diagrams showing the forces on the free body diagram. Second thing, write the forces acting on your mass, whatever they are. At that instant, the forces will be changing as your mass is moving, but at that instant, I would like you to write the forces in this form. The x component along the x-hat, the y component along the y-hat, in terms of their components. Bileşenleri cinsinden yazacaksınız ikinci şıkta. And the third one is just to find the relation between the tension, the length of the string, and the speed of your mass m.